All right, everybody, welcome back to CS 125. Hope you guys had a great weekend, finishing up MP4. Congrats to the blue team that wrapped up last night. The orange team is, I'm sure, on their way to finishing up by tonight. That's the end of the MP. You guys are done. That's a major milestone in this course, and I hope that as you approach that milestone and reach it, if you're part of the blue team, you stop to sort of think about how far you've come this semester and feel a sense of satisfaction, a sense of growth, a sense of progress, a sense of change in the abilities that you've acquired over the course of the semester and the ways that, the hard work and the practice and the dedication that you put into this class are paying off in terms of your ability to build cool things and understand new ideas and concepts. So today we're going to talk about our next sorting algorithm, which is a sorting algorithm known as merge sort. On Friday, we talked about insertion sort being a pretty classic imperative, programming sorting algorithm, right? We essentially kind of built a sorted partition of an array, one step at a time using a loop. Today, what we're going to do is we're actually going to look at a different approach that uses recursion on arrays, and an approach that achieves the best case sorting performance. So at the end of class on Friday, what we said is you can actually prove mathematically that even an optimal sorting algorithm, even in the worst case, should be able to sort an array of n items in n log n time. And we'll see where that log n comes from today when we analyze the performance of merge sort. Our insertion sort algorithm, unfortunately, in the worst case performance, ended up doing O(n) squared. And so that was a hint to us that we can do better. Today is one of the algorithms that we're going to look at this week. We'll look at merge sort today, and then on Wednesday we'll look at another algorithm called quick sort that both can achieve n log n performance in typical cases. All right, so let's talk about merge sort. So merge sort, what we're going to do is we're going to build up merge sort today in two pieces. Because what merge sort does is it harnesses this fact that if I give you, so sorting an array of unsorted integers is a challenge. It's something that, as we talked about last time and on Wednesday last week, people are still working on this problem. There's still active research going into not only new sorting algorithms, but new sorting systems that are built to sort massive amounts of data. So here's a particular approach that takes advantage of an interesting observation. That observation is that if I give you two sorted arrays, merging them together is easy. And in fact, that's a step that can be done in O(n) time. So if I give you two sorted arrays where the total size of the two is n, I can merge the two in O(n) time. And let's think about how their algorithm works. So here I have two sorted arrays. I have an array on top that's 4 integers long from 1 to 12. It's already sorted. I have another array on the bottom that's 4 integers long. And the question is, what's the algorithm for merging these two sorted arrays together to create a larger array that's also sorted? So let's look at it together. So again, it's easy. I shouldn't say easy. The algorithm is fairly straightforward. It gets a little ugly, but when we actually sit down and implement it. But conceptually, it's quite simple, right? So I give you two sorted arrays, and here's what I do. I look at the first element from both sorted arrays, and I choose the smaller one. That's the next item that I add to my merged array. So here what I'm doing is I'm looking at the first element from both arrays. In this case, again, we're sorting arrays of integers and we're sorting them into ascending order. So these two smaller arrays are sorted into ascending order. The smallest item in the first array is value 1. The smallest item in the second array is value 2. I choose the smallest value, which is value 1, and I stick that into my sorted array. And then I kind of shift that first array over. So now I'm looking at the next element. And I repeat this process. So now I compare the two smallest elements that remain in the arrays that I'm merging. In the first array, that's an element with value 8. In the second array, that's an element with value 2. Now I take the element from the second array. And I continue this process. So now I look at the two smallest values left in each array. I have 5 and 8, so I take 5. I have 7 and 8, so I take 7. I have 8 and 10, so I take 8. I have 9 and 10, so I take 9. Then I take 10 and I take 12. So what I've done here over the course of 8 steps is I've taken two arrays that were already sorted, I can't do this with unsorted arrays. This won't work. So if I take two unsorted arrays, this algorithm doesn't work. It harnesses the fact that if the arrays are sorted, the smallest item, in this case if they're sorted in ascending order, the smallest item will always be at the front. And so when I want to figure out which element to look at next, or which element to copy into my merged array next, I just look at the smallest item in both arrays. And that's the first item in both arrays. And so if you think about how long does this take? Well, each comparison, let's say, takes some constant amount of time. So I did one comparison, two comparisons, three comparisons, four comparisons, 5, 6, 7, 8. I did 8 comparisons, and then I also have to copy that value into the array. So to merge two arrays of size 4 takes 8 steps. That would also be true if one of the arrays was size 6 and the other was size 2. It sort of doesn't matter. It really depends on the size of the array that I'm going to create, or the total number of items that I'm are going to end up in my output array. Okay. So as our first fun imperative programming challenge today, let's actually implement this, because this is the first of all, this is the building block that we're going to use when we actually implement our algorithm to both to sort an arbitrary number of values, but also it's sort of a fun little challenge, right? So here I'm giving you the template for a function called merge, a static function. It takes 2 integer arrays and it returns a new array with the 2 values merged together. All right, so the first thing to do is let's handle some of our easy cases. If both arrays are null, then there's nothing really that we need to do here. We'll just return null because you gave me, and we could do other things to prevent these values from being null, but instead we're going to check, okay? Now, I have a couple of other cases to handle. I need to handle the case where the first array is either null or empty, but the second array is not. And I need to handle the case where the second array is null or empty and the first array is not. So what I'll do is I'll say else if first.length first is equal to null, or first.length is equal to 0. So I can check these two things together, remember, because of how Java evaluates OR statements. So if first is null, I will enter this conditional. This is the case where second is not null, because if both were null, I would have already returned as the result of this first part of my if statement. And the idea is if first is not null, then I know that first is a valid array and it has a length property that I can check. So that's what I check in the second part of this if statement. In this case, I can just return second right away, because I don't have any work to do. This is a case where you gave me a valid array second that might be empty or might have some values in it, but first is either null or empty. And so what I'll do is I'll say otherwise return second. And I have a very similar condition to check for second, which is second is null or second is empty, in which case I return first. Okay, so if I fall all the way through here, right? Actually, you know what? Let's add one more condition. We'll say else if first.length is equal to 0 and second.length is equal to 0, I'll return second. Well, you know what? Let's make this, since we're having fun today, let's make this a little bit trickier. So what we'll do is we'll say if second.length is less than 2. So if second.length is less than, nope. No, I can only do this. Okay. So now we'll go down here and we'll say else if first.length is equal to 0 and second.length is equal to 0, I'll return, in this case, I can return either first or second. So this is the case where you gave me 2 empty arrays, right? So now, and again, this is sort of a fairly involved check for invalid values because I have 2 of them and either one can either be null or empty. But now I'm getting to the point where I actually might have some real work to do. So in this case, I have 2 arrays and at least one of them is non-empty, right? And in fact, at this point, both of them have to be non-empty, right? If first is empty, then I would have already stopped here. If second was empty, I would have already stopped here. And I'm trying to think if I actually even need this condition. So if first is equal to, yeah, I don't need this because I already would have returned, right? So if both of them are empty, then I just would have hit this, right, which is fine. So at this point, I know that I have 2 arrays, first and second, and they're both non-empty. I know, it's Monday morning, we're all waking up a little bit slow, so it's taking me a few extra minutes this morning to, grab some tea and get my thinking cap back on. So anyway, so here we're done, okay? I know that was exciting. Let's go on. So at this point, what we actually need to do is write our loop that's going to copy things into this new array that we're going to create. The first thing we have to do is create the new array itself. So I'm going to create an array called, I'm going to say int to return, or I'll call it merged, and that's going to be a new integer array, and the size of this is first.length plus second.length, because it needs to be big enough to hold all the elements from the first array and the elements from the second array. All right. Now, what I'm doing is I'm essentially, if I go back and I look here, I'm essentially going through and I need to take, this is my first array, this is my second array, and I need to move those values one at a time into my merged array. And so there's really three positions here. This is a little, bit of tricky imperative code for us to write. Again, a good way to kind of like limber up on Monday morning. So there are three positions I need to keep track of. The first is my position in the first array. That's the location of the element in the first array that I haven't moved into the merged array yet. That should be the smallest element in that array. The second position is the position in the second array. So that's the index of the smallest element that I haven't moved into the merged array from the second array. And the third index is the position in the merged array. That's the next place I'm going to put the smallest element that's left. Okay, and again, inside this loop, this turns out to be a little bit complicated because there's a couple of different conditions I need to handle. Okay, so what I'm going to do is I'm going to say, I'm going to create I'm going to have the indices for my first and second array declared outside of my loop, and I'm going to use my loop index to refer to the index in the merged array. And this will make sure that my loop executes the right number of times, and I put something into the merged array at every point. So I'm going to say int first index is equal to 0, int second index is equal to 0, and then what I do is I do for int I is equal to 0, I is less than merged dot length I, and you know what? Let me call this something else. Merged index is equal to 0, merged index is less than merged dot length merged index plus plus. Okay, so yeah, checksales mad at me, but that's okay. I just want to make sure that line wasn't too long. So now I've got, again, I'm gonna do some work here. So I'm gonna go through, and I need to go through one by one, and there's a couple of different cases I need to handle. So the first case is if first index is equal to first dot length. And this happens when I've used up all of the values from the first array. So at some point, the first array is going to be empty. Or at some point, the second array is going to be empty. And one of them is going to empty before I'm actually done filling the merged array. Now, depending on the values that are in each one of them, one might empty way before I'm done filling the merged array. Let's say that my first array, all the values inside of it are smaller than the second array. So essentially what ends up happening is I pull all the values out of the first array first, and then I pull all the values out of the second array. So I need to handle both cases. I need to handle the case where the first array ends up empty before I'm done, and I also need to handle the case where the second array ends up empty before I'm done filling the merged array. So essentially what happens is if the first index is equal to first dot length, then this means my first array is empty, and that means I should move the item from the second array. So I'm going to say merged index is equal to second index, and then I'm going to do second index plus plus. So I'm taking the smallest value left in the second array, I'm copying that into my merged array on line 18, and then I'm bumping that index so that I move one step forward, right? So again, if I go back here, this step sort of corresponds to what happens here. So let's say the bottom one is my second array. I take item 7 and I move it into the merged array. And then I bump my index forward so that now I know that the next element I should consider is the element with value 10. Okay, I have a similar statement I need to write for the case where my second array empties before I'm done. And that is very similar to this one. Okay, so I'm going to say else if second index is equal to second dot length, So this means that my second index, this means my second array is out of values, and that means my first array has to still have values in this. Now, notice in these statements, I don't check to make sure that when I check my first index and I realize my first index it means that the first array is empty, I don't check the second index. And the reason is, I know that my outer loop's only going to execute merged.length number of times, and the way that I constructed my merged array is that it's the size of these two arrays put together. And so essentially, if the first array is empty and I'm still inside this loop, it means that my second array has values in it. And vice versa, if my second array is empty and I'm still inside this loop, it means that my first array must still have values in it. So now what I'm going to do is I'm going to say merged index is equal to first index, and then I'm going to bump first index. Okay, great. So yeah, we're warming up our imperative programming muscles. So at this point, I've handled the case where my first array is empty. I've handled the case where my second array is empty, but I haven't handled the case where both arrays still have values in them, right? And this is, if I go back here, this is the common case. So this is the normal case where I need to compare the smallest value in the first array with the smallest value in the second, okay? So the smallest value in each array is at first index or second index. And so now if I get down here, I know that first index is valid, and second index is also valid. So both of my arrays are not empty. And that means I need to compare the value at the front. So what I'm going to say is else if first index is less than second index, else. So I have two conditions here. So the first condition is the smallest element in the first array is smaller than the smallest element in the second array. In that case, what I do is I handle this very similarly to the way I handled this case up here. This case right here. I move an element from the first array into my merged array. So I say merged index is equal to first index, and then I increment first index, right? Otherwise, if I get all the way down to the else statement, what I know is that first index is not less than second index. So the correct item to move into my merged array must be the item in the second array, the smallest item in my second array. So now what I'm going to do is I'm going to say merged index is equal to second index. And I'm going to bump second index. So you can see in this code, there's actually a lot of symmetry, right? There's a lot of cases where I'm, handling one case for the first array, I'm handling another case for the second array, and they're very similar to each other, right? Like here, this is what happens when my first array is empty, right? I take something from the second array. Otherwise, my second array is empty, I take something from the first array. If the smallest value is in my first array, I take that value out and bump first index. Otherwise, the smallest value is my second array, I take that value out and bump the second index. Okay, now you might be wondering, why don't I increment the merged index anywhere? That's because the merged index gets incremented in my loop, right? So that's moving forward one step every time I go through the loop. So now the only thing I need to do here is actually, instead of returning first, return my merged array. And let's see if this actually works. And it looks like it does. That's pretty cool. So again, as always, let's test some corner cases. So make sure that it works if first is empty. Make sure that it works if second is empty. Let's put all of the smallest values in the first array and all of the larger values in the second array and make sure that it still works, and it seems like it does. Let's put all the smallest values in the second array and make sure that it still works, and it looks like it does. Okay, and so this is correct. Now, you can make this a little bit smaller and cleaner, remove a few statements here and there. But this is the gist of it, right? And there's really two parts to this, I would argue. The first part is this big block of error checking up here to make sure that I'm handling all the corner cases. Like if I get null, and again I can check the null cases here too. I could say this is null, make sure that we get the right thing. Okay, what about if they're both null? We're going to be good defensive programmers and make sure that things happen the way that we want, right? Okay, so this is good. Now, let's go back. Now, when we looked graphically at the operation of this algorithm on those little arrays, we kind of hypothesized that this was ON. But let's actually go and make sure that we're correct about that. Let's make sure that this is actually ON. Yeah, so there's a question in the, okay. So the question is, the checkup here already checks to see if it's empty. Yeah, see, I'm sorry. My terminology is a little bit confusing here. So the question was, if I'm already checking that the array is empty at the top of this statement, why am I saying I'm checking if the array is empty down here? So I'm not, what I mean by empty is that the array is 0 size. So if you pass me an array that doesn't have any elements, that's a special case that I handle up here at the top. Once I get down into this loop, I'm only in this loop if both of my arrays have elements. And what I mean by the array being empty is that all of its values have been copied into the merged array. So the array is not actually empty, right? First dot length here is not 0. Second dot length here is not 0. If first dot length was 0 or second dot length was 0, I would have already returned because I would have hit one of these if statements up at the top of my, my function. But what happens is at some point, once I have moved enough values from the first array into the merged array, every time I take a value out of the first array, I increase first index, right? I do that either if the second array is empty or if the first array has the smaller value. So at some point, first index starts off at 0, and at some point it's going to grow and grow and grow, and at some point it's going to get to be first dot length. Now it's possible that that's the last thing that happens and then I break out of the loop because the last value that I move into my merged array is from that first array. But it's also possible, like again, if I put all the smallest values in here, right? Let's try this. Then what happens is I'm going to put a print statement in here. This is a great question, by the way. Right? So what you'll see happened is that, and let's print the end. Let's print my merged index. Let's print that too. Okay. So you'll see what happened here. The first 3 times I went through the loop, the first 4 times I went through the loop, merge index 0, 1, 2, and 3, I copied stuff out of my first array, but then it was empty, right? So actually, let's print. Let's do this as well. Print then. We're going to print the merged index, and then put some colons in here, plus first index, plus second index. So again, they'll put some print statements in here. So you'll see that the first 4 times I go through the loop, the first index is the only one that changes, and that's because the smallest values are always in that first array, so I keep moving them one at a time. So again, I really shouldn't say that the first array is empty. What I mean is that we're done with it. We've moved all the values out of that first array into the merged array. So hopefully that answers your question and clears that up a little bit. All right, thanks for the question. Great question. All right, cool. So now let's look at the runtime of this. And let me pull out a little bit of our print statements just since this is already long enough and we want to kind of be able to gaze on it in full. I'm going to ignore these special cases up here. We'll just think about the runtime when we have some values in the array, right? So let's think about the runtime when both arrays are non-empty. So you'll see, I do, these steps are not going to change as the arrays get larger. These are just allocations that I have to do regardless of the size of the arrays. The part of the algorithm that scales with the size of these arrays is this loop right here. And you'll see that this loop is going to run merged.length times, where merged is the merge.length is equal to essentially to first.length plus second.length. So if I give you one array of size n and one array of size m, this merge function is going to take n plus n. And then the next thing, of course, we look for when we're examining implementations to try to understand runtime is we look at break statements, return, continue, that sort of thing. And there are none of those inside this loop, right? This loop has no breaks, no return, no continue, it just runs top to bottom. So this is an ON algorithm where n is the size, the combined size of the 2 input arrays. Okay. Now, this is kind of exciting, right? Because last time, we talked about sorting and we said, okay, well, we basically insertion sort in the average case is an O(n) squared algorithm. Now I have this O(n) algorithm that seems like it might be helpful for creating a sorted array. However, this algorithm only merges sorted arrays together. So now the question becomes, how do I use this as a building block to create a sorting algorithm? So far what we've done is we've implemented merge. Now what we want to do is actually implement merge sort. So actually, yeah, let's walk through the time and space complexity again. So worst case O(n), best case O(n), average case O(n). The merge step does not depend on any feature of the input. It's always going to run n times where n is the size of the first array plus the size of the second. That's nice. So how do we turn this into a sorting algorithm, right? That's the next step in this puzzle. And in order to do that, what we need to do is go back and reconsider this idea of array recursion. The recursion problems you guys did through that exciting week and a half where you guys only dreamt and thought about recursion on trees were typically on tree data structures. But as I pointed out, we can also write recursive algorithms that operate on other types of data structures, and we can particularly write recursive algorithms that operate on data structures that have this self-similar property. So remember, when I'm looking at arrays, if I take an array and I break it into two contiguous pieces, each one of those pieces is itself an array. So I have a big array here that has 8 values in it, but the first 4 values, the first 4 contiguous values, meaning they're next to each other, also constitute an array. So I can take this and I can break it in half into 2 smaller arrays. That first array I can break into even smaller pieces. So I can break that into 2 arrays of size 2. Each one of those size 2 arrays I can break into even smaller pieces. Now I have an array of size 1. At that point, that's my base case when I typically look at array recursion, because I can't take an array of size 1 and break it into any smaller pieces. Okay? So what we're going to do with array recursion is, just like with list recursion and with recursion on trees, we need a way to make the problem smaller, and we need to identify what our smallest subproblem is going to be. Remember, when we worked with trees, how we combined our results varied a lot, and that's also true with array recursion. We're going to look at one way of combining results with array recursion that leads to sorting as the result. But when we worked with trees, we combined results in all these different ways, but we had some common themes when we looked at tree recursion. We made the problem smaller by looking at the left subtree and the right subtree separately. And we typically identified the smallest subproblem as either being a single node or an empty tree, right? Because those were cases where it was typically very easy to immediately provide an answer to the problem. What's the size of an empty tree? 0. If I'm searching for a value, does it exist in an empty tree? No, right? Stuff like that. So with array recursion, how do we make the problem smaller? We split the array or the list into 2 smaller arrays. So if you give me an array of size n, my way of making the problem smaller is I say, okay, well, I don't know how to solve the problem on this big array with n elements, but what I'll do is I'll try to turn it into smaller problems. And I'll consider the first n over 2 elements and the second n over 2 elements, because now I have 2 smaller arrays. What's the smallest subproblem? So if I continue that process, I'm going to start from a big array and I'm going to make smaller arrays and smaller arrays and smaller arrays, but eventually I have to solve the puzzle. I have to get to a point where I have a problem that's small enough that I can't not solve it. And with an array, the smallest subproblem is typically an array with a single item. Okay? So now, how do we turn this into a sorting algorithm? So we have some of the pieces that we need, right? We have some of an intuition about how to write recursive algorithms on arrays. And it turns out, remember that there's that third missing piece. How do I combine the results? Well, we've just implemented merge. Merge takes 2 smaller arrays and combines them into a bigger array. And so it turns out, suddenly, I have everything I need to write a recursive sorting algorithm on arrays. So here's how it's going to work. This is called merge sort. It's a recursive algorithm. The base case is we've reached an array with a single value. An array with a single value is sorted. So all we do is return it. We don't have to do any work. This is our base case. Once you've taken a big array and you've broken it down into pieces that are so small that there's only 1 item in it, you don't need to sort anything. An array with 1 item is sorted. My recursive step is that I take a big array and I break it into smaller pieces. And I try to do this into roughly equal sized pieces. So if you give me an array with size n, I try to break it into an array with size n over 2 and an array with size n over 2. And again, this can be tricky because arrays might have odd number of elements or whatever, but this is what we try to do. And you'll see why in a few minutes when we analyze the runtime of merge sort. How do I combine the results? Merge. I just wrote the way to combine results. So I've actually done most of the work, right? The tricky part here is actually merging those two things together. When we actually get to the part where we're writing merge sort, you'll see that it's actually not too much code that we have to add to complete the job. All right, so in our merge sort implementation, we're going to use a couple of helper functions from the arrays library. So Java has an arrays class that provides some helpful static methods for doing things like partitioning arrays. Now, could we write our own functions that would split an array into two pieces? You could, but why bother, right? Let's just use the ones that are built in. That's not the interesting part of this problem, right? The interesting part of the problem is seeing how the structure for the sorting algorithm emerges, okay? So specifically, we're going to use a function from the arrays library called copy of range. And this gives me a copy of a particular part of an array. And I'm going to use this to divide the array into two parts. I'm going to divide the array into an array of size n into an array of size n over 2. That's the first n over 2 elements, the first half of the array. And then an array of size n over 2 that's the second half of the array. Okay, so let's do this. So merge we've already got. I'm too lazy to implement merge again. I'm just going to go back and get it because we already did it, right? We've implemented merge. Life's too short to implement it twice. Well, you guys will get to implement it a few more times. With practice, I am not going to challenge myself here to implement this again, even though my brain actually feels warm now, so I probably get it right. But why take the chance? So we're just going to cut and paste. So now we have merge, right? How do we do merge sort? So merge sort is going to end up being a recursive algorithm. So just like with other recursive algorithms, we approach it in the same way. I know it's not on a tree, but let's not let us scare us, okay? So here's what I'm going to do. First thing I'm going to do is I'm going to say if the size of my input array is, I'm not going to worry about null. You could, but the way that we set this up, we can make sure that this never gets called on null. So let's not worry about null for now. Instead, let's worry about cases where the size of my input array is less than 2. So this means either I have an empty input array or I have an input array with size 1. In either one of those cases, I don't need to do any sorting. I'm already done. So what I'll do is I'll just immediately return the input array. So this is my base case. This is just like when we did tree recursion, writing the case to check if I'd had hit an empty node or if I'd hit a leaf node, okay? If I haven't gotten to that point yet, I still have work to do. I have to make the problem smaller. And so now what I'm going to do is I'm going to, essentially kind of like, I'll think about this in terms of the left and the right half of the array. So the first thing I'm going to do is I'm going to say int left is equal to array, and I think, did I input this? Yeah, or import this? Yeah, okay, so I'm going to do arrays dot copy of range, and now I kind of have to input array, and I want the values from, I want the first half of the array. So I'm going to do input array length divided by 2. This will give me the first half of the array. So that's the left side of my array. Now let's get the right side of my array. So this is the second half, the last set, okay, input array. I'm going to go from input array dot length divided by 2 to input array dot length. Okay, let's try this just to make sure that say array brackets at legal position. Oh yeah, I want them over here. Sorry. You can put them there, but that's an old way of doing it. That's wrong. Okay. So now what I've done is I've divided my array into 2 parts. But what I really need to do is I need to actually then solve those smaller pieces and merge them together. So how do I sort an array of size n over 2? Well, I call merge sort on that array. I'm going to do merge sort, and I'm going to pass it this smaller array that I've just created. I'm going to do the same thing here. I'm going to call merge sort, and I'm going to pass, let me see if I can make this prettier. I'm going to pass this smaller array that I've just created. So now this is my recursive step, right? I said I don't know how to sort a big array, but I do have something that should be able to sort a smaller array. So I divide the array into two parts and sort those smaller arrays. Now, how do I combine the results together? Okay. I have this merge function, right? Merge takes two sorted arrays and combines them into one bigger array. Right, so now what I'm going to say, I'm going to say int star result is equal to merge left, right. And then I should be able to return that from my call. Okay, and let's see what happens. Ooh, look at that. When stuff like this works, it's just like magic, right? Okay, so let's pause and try to figure out what just happened here. Let's just leave this alone. We know merge works. We've worked with that already. Let's focus on merge sort here and try to understand what's happening. And actually what I can do, let's make this just a little bit cleaner. You can actually combine this whole statement into one, right? So I can actually write this entire thing as one call, but for the purposes of not making it like terribly, terribly finicky, let's just leave it this way, right? So I sort the left part of the array, I sort the right part of the array, and then I combine the two results by merging the two sorted arrays together. In order to see how this is working, what I want to do is let's put a print statement in here, and let's print the size of that array that I'm trying to sort. And what you'll see happen here is the first call, so I start off by trying to sort an array of size 8. And essentially what happens is I print that size. It's not small enough that I'm done. And so now what I do is I call merge sort on the first half of it. And so now I'm sorting an array of size 4. I see the second print. So that's also not small enough to finish the job. So I divide it into two arrays of size 2, and I start sorting the leftmost array of size 2. And in fact, let's do this. Let's print the input array.length, and then let's also print input array 0, the value at the front. Okay, because this will show us where we are in the array. So the first time through, I'm trying to sort an array of size 8 that starts with value 8. That's the whole array. The second time through, I'm trying to sort an array of size 4 that starts at value 8. That's the first part of the array. The third time through, I'm trying to sort an array of size 2 that starts at value 8. That's only the first two values. I'm always starting with the left, remember? This part of my code means that I will always try to sort the left part of the array first. So finally, I get to this value with item 1, and now what you'll see is, now I'm done, okay? So the first thing that happens is I sort the array with only one value in it that contains 8. And then I sort the array with only one value in it that contains the value 5. But now I need to work on the right side of this. So I go down, and now I'm sorting an array of size 2 that starts with 7. And now I sort the array of size 1 that starts with 7. That's a single element. I'm done. I don't need to do any more work. That's my base case. Now I sort an array of size 1 that contains 3. Okay? So now I'm done with that. Now I'm actually going to go and start on the second part of the array. So now I start with the array of size 4. I break that into two smaller arrays. The left side has an array of size 2 that starts with 4. And then I do that all the way until I get an array with a single value that's 4, and I'm done. Array with single value that's 1, then that contains 11. And I proceed this way through the rest of the array. Right? So now what we'll do is so that's essentially how I'm breaking this down. Okay. When I'm merging things together, let's do this. Let's and then I think there's a way to. Is there? I think arrays has a print function. That's angry with me. Okay, that's all right. Yeah. Let's see. Is there a? Yeah, there's a toString method. Okay, so that'll help me print the array. So we'll do arrays.toString merged, and then I'll return it. All right, so now you'll see once I've sorted the array with size 1, which was already done, and I've sorted the array with size 1 that contained 5, now I merge them together. And so now I've completed sorting 2 values, just that first little part of the array. Then I do the same thing with this guy. And when I'm done, I've sorted the second little part of the array, the second pair of values. So I sorted the first pair of values into 5 and 8, and I sorted the second pair of values into 3 and 7. And then I merge those 2 results together. And remember, I have this fantastic merge function that runs in linear time that can combine 2 sorted arrays. I do the same thing in the back of the array. So now I've sorted the front of the array. So I have 3, 5, 7, and 8. That's the front of the array sorted. Now I need to work on the back part of it. So again, I start with the array with 4 values that starts with 4. I break that down until I get to pieces that are size 1 that I don't have to sort. And then I start merging. So I merge the first 2 together. They're actually in the right order. I merge the last 2 together. They're actually in the right order. Then I assemble the second half of the array into a merged second half of the array. So this is the last 4 values in the array sorted, because I've now merged things together properly. And now I've got an merged array of size 4 and a merged array of size 4, and all I need to do is run my merge function one more time to bring those together into the final result. Okay, so it's pretty cool. We implemented merge sort. It's kind of fun. Now, what we want to do is we want to actually think about the runtime. And this is tricky. This is what we're going to do for the rest of the class, because this is a little subtle. And so I want to give you guys some time to absorb this. So again, I've got this. I think it works. You can experiment with some other values. I think it does the right thing. But how long does this take? So we know that this merge step always takes O(n), where n is the size of the arrays that we're merging, the total size of the array that results from the merge. What we don't know is how many times this gets called, and we also want to think about what size arrays are being merged together. Okay, so let's do this in an array of size 8. Using powers of 2 here typically helps. If you wanted to do this on an array of size 16, it would work very similarly. If you want to do something like an array of size 12, it starts to get a little messy, but it's roughly the same. All right, so the first, and what we're going to do is we're going to think about the merge steps, right? In terms of how many merges are being done and what are the sizes of the arrays. So the first merge that we did, so we got to the point where we broke things all the way down and then we started combining our results together. The first merge, we merged 8 arrays, 8 arrays of size 1 into 4 arrays of size 2. So the runtime of that is 4 O(n) merges where n is equal to 2. And that essentially works out to O of 8, right? Where 8 is the size of the entire array. The second merge that we did, stay with me here. Well, there's a picture coming. The second merge that we did, we took 4 arrays of size 2 and we merged them into 2 arrays of size 4. So remember, the time for the merge depends on the output size. So I have 2 O(n) merges where n is 4, which is equal to 1 O(n) merge where n is 8. The third merge, this was our final step, we took 2 arrays of size 4 and we broke them and we merged them back together into 1 array of size 8. So this is 1 O(n) merge where n is 8. What you'll see here is that at each level, we're doing the same amount of work. The first merge, where I went from 8 arrays of size 1 to 4 arrays of size 2, I did 4 merges with an output size of 2. So 4 O(n) merges where n is 2 is 1 O(n) merge where n is 8. That's 1 O(n) step where n is 8. The second level, I did 4 merges of size 2 into 2 arrays of size 4. So the output size is 4. I did that twice. So I ended up with 1 O(n) step where n is 8. And the last step, I take 2 arrays of size 4, put them back together into 1 array of size 8. So I've definitely got 1 step where n is 8. 1 O(n) step where n is 8. So, and now how many merges did I have to do? Well, I was doing an array of size 8 and I did 3 merges. And it turns out if I was doing an array with size 16, I would do 4 merges. If I was doing an array with size 32, I would do 5 merges. Because, and this has to do with how we broke the problem down. Remember I said that we always want to, when we break the arrays apart, we want to create arrays that are the same size. Because what that means is that I make the problem half as small, half as small, half as small, half as small. And if I do that, if I start with a certain number, the question is how many times do I have to do that before I get to those arrays of size 1? And the answer is log n. So if I take 8, divide it in half, I get 4. That's 1 step. Divide it in half, I get 2. That's 2 steps. Divide it in half, I get 3. Sorry, I get 1. That's 3 steps. If I took 16, divide it in half, I get 8. That's 1 step. Divide it in half, I get 4. That's 2 steps. Divide it in half, I get 2. That's 3 steps. Divide it in half, I get 1. That's 4 steps. So the amount of time it takes me to break things down to the point to where I get to arrays of size 1 is log n. So I have log n levels. Every level I do O(n) work, I end up with n log n. It's actually kind of a beautiful result, right? I've always liked this. All right, let's look at the picture. So here, essentially, you think I had, these are my 8 arrays of size 1. 1, 2, 3, 4, 5, 6, 7, 8. And I merge them. Each one of these merges, I have 1, 2, 3, 4 merges. Each merge created an output array of size 2. That's equal to 4 times 2, which is 8. So that's my first step. Then I took these 1, 2, 3, 4 smaller sorted arrays, and I merged them into 2 larger sorted arrays, each one that had size 4. So again, 2 merges into arrays of size 4, so that's equivalent to an O(n) step where n is 8. So I had an O(n) step to get to level 1, I have an O(n) step to get to level 2, and my final O(n) step is taking those 2 arrays of size 4, bringing them together to 1 array of size 8. So merge sort, sorry, I'm getting a little ahead of myself. So merge sort actually accomplishes the goal that we had, which is that we wanted a sorting algorithm that would be able to run in O(n) log n. And this is it. When we talk about quicksort on Wednesday, we're going to talk about some of the problems with merge sort. So merge sort is not without its weaknesses. This is why there are other sorting algorithms. You might think, well, okay, I found the sorting algorithm that runs in O(n) log n. Why do I need to keep going? Well, the answer is because there are better ones. There are better ones because some of them actually will run faster in good cases, and also because some of them will take up less space. So one thing to look at, one thing to just sort of consider about merge sort. We already talked about the fact that the merge step always takes O(n). There is no best case, worst case, or average case for the merge step. They're all the same. Or actually, I shouldn't say that. There's a best case, worst case, and average case for the merge step. They're all O(n). The same thing applies to the recursive part of my algorithm. This is always going to take log n levels where n is the size of the array that I'm sorting. And so the great thing about merge sort is that it always takes O(n) log n. The terrible thing about merge sort is that it always takes O(n) log n, because there are cases where when the array is sorted, I shouldn't have to take n log n. Think back to insertion sort even, remember? How long did insertion sort take when the array was already sorted? O(n). And so it's clear that in certain cases, I should be able to do better. It turns out that checking whether an array is sorted is an O(n) operation. So again, great thing about merge sort, it's predictable. It always performs in the exactly same way. It's always going to take O(n) log n. The terrible thing about it, it's always going to take O(n) log n, even on inputs that other sorting algorithms would be able to process much faster. Okay, so that's the end of our argument today about merge sort. I always find it kind of satisfying when we can kind of do like one topic in a class, so that was enjoyable today. We did merge sort from top to bottom. Again, congrats to the blue team for finishing up MP. The orange team will wrap up tonight. We will release the final project write-up tomorrow. So that'll be what you'll be doing in lab tomorrow, is that you'll be looking at the final project write-up. You'll be finding a partner. So this is a lab that you'll actually have to participate in terms of like either on the forum or through Zoom or whatever, locating a partner. We are going to relax the requirement this semester that you work with someone in your lab section, because we're not meeting in lab anymore. But that is what we'll be doing in lab tomorrow, is that we'll be doing startup with the final project. We'll do the lab on sorting and searching next week, and then you'll return to your final project a week later. And the week after that in lab to both have a checkpoint to make sure you're getting started, and then to assess the final project during the lab during the last week. So I hope you guys are all well. Take good care of each other and the people around you. Stay safe. We'll be back on Wednesday. We have a quiz. I'll be here at 11 o'clock talking about quicksort. You're welcome to join me. And I will look forward to seeing you all again on Friday.